Hey everyone, I'm Raghav, and in today's video, we will talk about all the four problems from the Leetcode Contest 388. This is the first problem. The problem name is Apple Redistribution into Boxes. The problem says that we have been given an array apple of size n and an array capacity of size m, and there are n packs where ith pack contains apple I, number of apples, and there are m boxes, and the ith box has a capacity I, this many apples, and we have to return the minimum number of boxes which we need to select to redistribute these n packs of apples into the boxes. And the apples from the same pack the apples from the same pack can be redistributed into like multiple boxes as well. So like this was just a clarification um, for an achieve. Like we will see what the problem says. In a nutshell, the problem says that we have been given an array within apples. Maybe there are values like 5, 4, 3, 7, which denotes the number of apples in a pack. Like apples of 1 will, like here it is 4. It means that in the second pack, basically the second element is denoting the second pack, there are 4 apples in it, and we have been given some boxes with the capacities in the, like their capacities have been given in the array capacity. It can be something like 7, 2, 6, 4. Let's say it is like this. Here it denotes that there are 4 boxes. The capacity of the first box is 7, capacity of second box is 2, capacity of third box is 6, and the capacity of fourth box is 4. Something like this. And what we have to tell is you can choose uh, some of these boxes and put up these apples. Like you have to put up all of these apples into some of the boxes which you chose, and such that all of the apples should be contained inside them. So, in a nutshell, the problem is asking that you have been given these many apples, like the sum of these, uh, 9, 12, 19, I guess. Yeah, 19 apples. You have 19 apples. You want to choose some of these boxes and put up these 19 apples there. And what you want is the sum of capacities of the boxes you have chosen should be greater than 19. So, you have to choose some boxes, and the sum of capacities of those boxes should be greater than 19. That's what we have to do. And it's up to us which boxes we choose. We at the end have to tell the number of boxes which we require to choose. So I think that this one is a pretty simple one. It is obvious that, like, first of all, let's just see the try run there, like what you should do. Okay, in this case, you will have to choose all 4 of the boxes. Let us say there was one more box with capacity 10. So if I choose this guy, this guy, this guy, this guy, in that case, yeah, sorry, one mistake. The capacity should be greater than or equal to 19. So here in this case, the capacity of these boxes is equal to 19. So if I choose these boxes, I will be able to just contain all these apples, and I will get my answer as 4. But I have to return the minimum one. I have to return the minimum number of boxes I need. So is it a good idea to choose these? Or would it be a better idea to choose 10 in place of 6 and 4? It will, like, have one lesser box than this, right? I hope that you got the idea that if you choose a larger box, it will have a larger capacity. So at the end of the day, you might use some lesser number of boxes. Similarly, choosing the box with capacity 6 makes more sense than choosing the box with capacity 2. Here the capacity of these 3 boxes is greater than equal to 19, so our answer will be 3. Right. I know that I over explained a bit, but I think that it's a good idea to explain more on the A problem. Please give your feedback for this explanation in the comment section. That what do you think? Should I explain this much or just keep the solution short for a problem also. Okay, so now let's come back to the solution. The idea which we have got is that for um, like what we can do is just sort the capacity, the array of capacity, and find out the total number of apples. Let me call this as sum for now. Sum equal to the total number of apples, which is nothing but the sum of all the elements in the array apple. And after that, what I can do is I can just go on from I equal to n minus or maybe m minus 1. Like let us say um, the size of the array capacity is m. Then what I can do is I can just start from m minus 1 since I want to start from the largest guy. I want to pick up the largest box first. So I can just have a for loop from the back going on till the front and just say here I will say sum minus equal to the capacity of I, basically just reducing, or maybe you can just have some if else conditions. You can have some if else conditions that hey, if the sum, like sum is nothing but the remaining number of apples which you have to put them in some boxes, if this thing is greater than um, the capacity of I, in that case, just reduce the value of sum, just reduce the value of sum and increase the answer, where answer is the number of boxes you require, which was initially 0. And in the else case, yeah, answer would still be incremented, and now sum will actually become equal to 0, and then you can break. And if you want, you can just write up some if else conditions like these in any way you like. I wrote a fewer less lines by having some if else conditions in a different way. I will show you later on, and then at the end you can just return answer. So this is how I think a beginner could have approached the problem. Obviously, there are some better ways of thinking about the problem. You could have thought about it in different ways. But I believe that the way in which we have discussed so far is something a beginner can think in. Like uh, that's what I think a beginner can approach. There is one more thing, like you might have a doubt that what if the sum of all these elements is less than the number of total apples I have? In that case, I would not be able to put up all these apples in the boxes. So yeah, this is a valid doubt. You should get these kind of edge cases in your mind. The problem has actually specified that the inputs would be generated in a way that it is always possible to redistribute, which means that the sum of the capacities would be greater than the sum of the apples. So here is my code. I first of all stored the sizes in NNM so that I don't have to write up this whole thing again and again. I will just write NNM instead of that. Then I sorted the capacity vector and I found out the number of total apples by using an STL function. If you want, you can just run up a for loop for this. It's up to you. And then I created an answer variable. Again, this is something you don't necessarily need to do. At the time of breaking, you could have just returned it. Let's leave it for now. I think that this is easier to understand. In case if the remaining apples which I have to put is less than or equal to 0, basically the capacity, the total capacity I have taken so far with the boxes I have chosen is greater than the number of apples. In that case, I just break. Otherwise, I will increment the counter and subtract the capacity. Like in case if this looks a bit harder to digest, then no problem, just come back. We did discuss about an easier way, like an easier way to think about. Just write up two if else conditions to inside the for loop, right? And this is something you can actually explore. Like writing shorter code is a really good thing, which you should try to do. It will make you faster in contest. So I believe that it should be good enough. Let's talk about the time and space complexities. We are not creating any extra space, right? We are not creating any, we are not having any extra space, any sort of vector or structure. So the space complexity would be big O of 1. In reality, it is not really big O of 1. The sort function also takes some space. I think it should be big of login, but in general we do ignore it. Like you will see mostly people just ignore that space. So for now, that's why I'm saying big of one. Though actually it also takes some space, which is obvious. Like we have studied about sorting algorithms. Almost all the algorithms take some space, and whatever quick sort or not sort, like whatever algorithms are being used, they also take space. So eventually the space comes out to be big of login. And for the time complexity, sorting will take big of n log n, right? And this will take big of n, which is less than log n, so I'm not writing it there. And this is also big of n. So the most dominant like the most dominant thing here is just the sort function, which will take big of log n log n time. So this is the time complexity here. Let us go to the B problem. Now for the B problem, like it is similar to the A1, like the solution is almost only that much harder. But I think that um, for a B problem, this is a bit easy. Like generally B problem can be a bit more hard. So what we have been given here is, first of all, the name of the problem is maximize happiness of selected children. We have been given an array happiness of length n and a positive integer k, and there are n children standing in a queue where the ith child has an happiness value of happiness I. You want to select k out of these n children in k turns such that in each turn when you select a child, the happiness value of all the children that have not been selected till now will decrease by 1. Note that the happiness value cannot become negative. Basically, if it is equal to 0, it will just remain 0. And we have to return the maximum sum of the happiness values of the selected children, which we can achieve by selecting k children. So in a nutshell, the problem is there are n children, an array is being given which tells about the happiness of every child, and we have to choose we have to choose uh, k children out of these. We have to choose k children out of these. Um, in one turn, we can choose one child, and we have to do k turns, so we will choose k children. And let us say I choose a child. Maybe let me take an example. Do a small try run. It will make the problem a bit more easier to understand. 7, 4, 6, 10. Maybe something like this. The array is looking 3, 4, 7, 6, 4, 10. Maybe like this. And k is equal to 3. So what you have to do is you have to choose three children. Maybe you choose this guy first. Once you choose one guy, all the other people whose happiness value is greater than 0 will get reduced by 1. So after this, once you choose the guy, the array will become 2, 3, 5, 3, 9. And since you have chosen this guy, I'm not writing it again because you cannot choose it again. Now, from the remaining ones, let me say that you chose 7. Now you have to choose another guy. Like we have to choose k children. है ना? So let us say you chose this guy. So you will get it added in the happiness value. Like the happiness value would be added, and this guy would be removed. All the other people will get their values decremented by 1. Their happiness will be decreased by 1. And now let us say you chose maybe this guy. So it would be removed, and the happiness values of all the other people will be reduced by 1. Sorry, it should have been 8 earlier, and now it will become 7. Um, yeah, by mistake I wrote it 10 here, which had got reduced to 8 earlier. Yeah, basically we got this much happiness, right? We got 7 plus 3 plus 2. And what you want is you want to maximize this value. So since we want to maximize this value and it is up to us what children we choose, I think it should be quite intuitive for us to choose the maximum value. At least try to think about it. What if we choose the max value? What if we choose the max value from the array? Like this is something I feel that it should be intuitive even for a beginner. If you want to maximize your sum of the k children you chose, like the sum of happiness of the children you chose, if you want to maximize this thing, then why don't you choose the person with the maximum happiness? This is something which does come to my mind, and I believe that it should come up to even your mind. From there, you might get like you got the idea that what if I had chosen the person with the happiness 10, then the person with the happiness 7, which would have actually get reduced to 6, and then the person with the happiness 6, which would have been reduced by 2, because in the first turn when you chose the 7, everyone's happiness got reduced by 1, and when you chose this 7, which had got which had became 6 by that time, everyone's happiness reduced once again. So the person with the third highest happiness, which was 6, would now be 3, would now be 4, right? Yeah, like there is one more thing. I think it's not hard, but let me just talk about one more thing. If the array is initially 7, 3, 4, 7, 6, 4, 10, and let's say you chose this biggest number, after this, all of the people will, yeah, all of the people will reduce by 1. Like all the values will reduce by 1, but the values which, since this guy was earlier greater than this, even after reducing 1 from all the values, the largest guy, like the second largest guy, which was initially in the original array, would still be the second largest guy in the new array. है ना? Similarly, this guy, since it was smaller than this, it will still remain smaller, and it will remain greater than the other people even after reducing 1 by everyone. Like you will just take, yeah, this is something very obvious. Why did you spend time at talking about this? Uh, but I think that we should at the very least get these ideas in our mind. It won't take more than maybe 5-10 seconds to verify this in our mind, but uh, this is something we should think. So that is why I discussed this. Now coming back to the idea which we had got, like if I was a beginner, I would have definitely got this idea. I would have got one doubt in my mind that uh, how does it guarantee me कि I will, like, this will be my answer, or basically uh, is there some way for me to logically to just satisfy myself, yeah, what I'm doing actually makes sense. And one more thing, that can there be some better, like can there be um, like instead of choosing 10, 7 and 6, like this guy and this guy, if instead of choosing these guys in this way, 1 2 3, if I had chosen them in the way like 1 2 3, will the answer be same or different? Again, this is something really easy to verify, but you should get these questions in your mind. It will actually make you better at finding patterns and uh, basically indirectly competitive programming also. So even if you had chosen something like um, 6, then after that 10, and then 7, still the answer will be same. If you see, the order in which we pick up the elements doesn't really matter, because let us say you chose the k largest 3 elements, the k, sorry, if you just chose the k largest elements from the array, then your answer will be equal to um, the sum of k largest elements minus, like you can just say this thing as 10 plus 7 plus 6 minus 1 plus 2, just clubbing up this minus 1 minus 2 together. Similarly for this guy, it will be nothing but 6 plus 10 plus 7 minus 1 plus 2. So in that way, you see that the, like if you just decided that you will choose the k largest elements, then it doesn't really matter in which order you chose them, because the answer would at last be equal to sum of the k largest elements you chose minus the sum of first k minus 1 natural numbers, right? The sum of first k minus 1 natural numbers. Yeah, by the way, this would be true even if you don't just choose the k largest elements. Like for any k elements you choose, the answer will be like the sum of those elements. Happiness would be equal to the sum of those k elements which you have chosen minus the sum of first k plus k minus 1 natural numbers, considering that the happiness value never goes negative here. Like there's one more case. What if you had the two children as 1 and 1 and you had k equal to 2? Basically, you have to choose both these people. So if you chose this guy first and then this guy, then you will get 1 first and then you will get a 0. Maybe let us say there was one more and k was equal to 3. I hope that you are getting the idea which I am discussing here. We have already, like I believe that you would have already got the solution. I'm just picking up a few doubts which you might get. Just I'm trying to consider that what a viewer might get a doubt, and I'm talking about that. So you might get a doubt like this, yeah, here the sum would be just one, because first you will choose this guy, the other people will become 0 and 0, then you chose this guy, so this guy 0 will not be reduced since the happiness value cannot go negative, and you will get a 0 here. So you might just feel yeah, in this case this formula would not work, है ना? The formula which we had created will not really work there, because according to formula the sum will, like the answer should be 3 minus the sum of two natural numbers, which is 3, which comes out to be 0, because basically here this 1 plus 0 is not equal to, like this is not equal to 1 plus 1 minus 1 plus 1 minus 2. It is not equal to that. It is here 1 plus 1 minus 1 plus the other value became larger, so it is 0. So yeah, the formula is not really completely accurate, but we just got some idea from it. If um, like we were just getting some intuition, something like this, the formula is not 100% accurate, so we won't go with the formula. Like we just found a case where it is failing as well. So what we will do is just sort the happiness array, sort this happiness array. Maybe let's say reverse sort it, like sort it in the reverse way, or just sort it and then reverse it, so that the larger values are coming first. Obviously, it doesn't really matter. You can have larger values coming at the end also. It just needs to be sorted. And after that, for I equal to 0 till I is less than k, for the first k elements, initially you can have answer equal to 0, and then here you can say, like inside the loop, you can say answer plus equal to the maximum of 0 comma happiness of the ith guy minus, um, like for the first guy 0 should have been subtracted, for the second guy 1 should have been subtracted from his happiness, for the next guy 2 should be subtracted from the happiness, which you see that it is like I is always equal to that, so you can say it as happiness of I minus I. If you had been doing one based indexing here, then you would have been writing happiness of I minus I minus 1, because what you want is the first, from the first guy 0 should be subtracted. So you can try to play around it, that what if you are having a zero based indexing or one based indexing, because at the beginning level getting out of this kind of silly mistakes is really important. Otherwise you might just make up some silly mistakes in future. So I will recommend you to play around it, that what if the loop was from 1 to k, if it was from 10 to k plus 10, like till which point should it be. Try to think about these cases, and this is actually the point we are practicing. You are practicing so that you get more comfortable at coding, है ना? So remember that solving the problem is not the motive. Solving is not the motive. The motive is to focus on such cases ki yaar, like in the first problem we did discuss about what if capacity is less than the sum of apples. Talking about or thinking about those cases is the more important thing here. I believe it should be quite clear now. Let me show you my code. The code is pretty simple. I'm just first of all sorting the array, sorting the happiness array. Then I'm going from, like for every element, the current happiness of this ith person. will be equal to the happiness I minus I, since it cannot go below 0. I'm saying max of 0 comma happiness of I minus I, and after that I'm just adding its happiness, adding the happiness of that guy to my answer. That's it. Here the space complexity will be equal to big O of 1, because we are not using any extra space. Again, let me remind that sort function will take up some space, but we generally ignore it. Like I see that mostly people generally ignore it. That is why I'm not mentioning it here. But some people, I have at some places, I have seen that people actually mention it to be login. I have seen this thing, so that is why I'm just mentioning it, but not really writing it. And for the time complexity, it will take big O of n login, and this loop will take um, big O of n, sorry, big O of k, and we know that n is already greater than k, so this thing would be dominant. That is why, is it? No. That is why I will say that the time complexity overall is big O of n log n. Yeah, I hope that this problem is also clear. Now coming up to the third problem. Now I'm having a little bit of expectations from you. I won't go with a very basic explanation like the first, in the first two problems we had a very basic explanation. Um, I will expect that now you know about STL and some stuff like that. You have some practice. So I would spoon feed less now. The third problem, shortest uncommon substring in an array. The problem says that we have been given an array of size n consisting of n non-empty strings. Find the array answer of size n such that answer I is the shortest substring of ARR I. And again, let's see from the very start once again. We have been given an array, like there is no problem with it. It is having some non-empty substrings. And then we have to find some answer array, which we will have to return at the end. Now let us see how will you find out the answer array. Answer array, like sorry, not answer array, but answer of I. The answer for the, like, in the answer array, the ith position will have the shortest substring of answer of I that does not occur as a substring in any other string in array. Um, yeah, so basically, if you talk about us, okay, first of all, let's read it completely. If multiple such substrings exist, then answer I should be the lexicographically smallest, and if no such substrings exist, answer I should be empty. So first of all, I'm expecting that you know about lexicographically smallest. Let me just have a quick like revision of it. Um, for now, you can just understand lexicographically smallest as the number which comes first in the dictionary, like ABC. A word like ABC will come before ABCD or before ABD in a dictionary. So this guy is lexicographically smaller than this, and ABC will come before ADB or ABD, whatever. So this is lexicographically smaller than that. So like my name Raghav is actually gonna be lexicographically, or like Leetcode would be lexicographically smaller than my name Raghav, you know, in a dictionary. So similar to that, we have lexicographically smaller and larger numbers. Obviously, here there is a catch that a number like capital R, like name starting with Raghav, maybe capital R, a word starting with capital R, would be considered lexicographically smaller than the word ABC. Like R is lexicographically smaller than A, so this would be smaller than ABC. But for now, we don't really have to worry about all that. In the problem, we just have, um, let me see, we just have lowercase English letters. So you don't have to worry about small and uppercase letters, lower and uppercase letters. Just see, we have to find out the shortest substring of error I. What do we mean by the shortest string? A string with a shorter length. So if you have something like ABC and maybe AABD, here AABD is lexicographically smaller, but it is having a length of 4 and it is having a length of 3. So we will pick up this one, the one with the shortest length, right? If we have like we will see how to find out these strings, but let us say that you found some strings a b c d a b c a b d and z. So here, first of all, and maybe if you found some string like c also, and maybe x, like whatever. So first of all, we will say the strings which are having the shortest length, we will have our answer from one of these. So we will just forget about all of the strings with a larger length. Now among the one which are having the shortest lengths, we will see here like which one is the lexicographically smaller one. C is the lexicographically smaller one, so this will be our answer. So I hope that you got the idea of how to find out the answer. Once we have found out the substrings of ARRI that does not occur as substring in any other string. Let me take an example here. CAB, AD, PAD, and C. Let us say if we are having these three strings. Now, what we have to do is for every string, like out of all the substrings which it has, like what are the substrings which it has? C, A, B, C, A, B, C, A, B. These are the six substrings it has. Out of these, we want to find out the shortest one which does not come as a substring in any other string. Like, does C come as a substring somewhere? Yes, it does. What about A? Yes, it does. What about B? Yes, it does. What about CA? No, CA does not come as a substring anywhere. So, yeah, CA is one of the substrings which can be my answer. What about AB? Does AB come as a substring? Like, does AB come as a substring in any of these strings? No. So, AB can be my answer. And what about CAB? Like, CAB also doesn't come anywhere. So, CAB can also be the answer. Now, we know that these two are having length of 2. So, just forget about this one. Our answer will be one of these. And yeah, these cannot be an answer either. Among these, the lexicographically smaller one is AB. So, this will be our answer. And yeah, the answer here is AB. Similarly, for AD, you can see A is coming up. Like in AD, there are three substrings A, D, and AB. We are not counting the empty substrings for now. Now, A does come as a substring at multiple places. D also comes as a substring here, and AB also comes as a substring here. So none of these can be the answer. If you don't get any string which can come up as the answer, then you will just return an empty string like this. Then in the third one, you have six strings again: B, A, D, B, A, D, and BAD. These are the six substrings. Now, B is coming as a substring here. A is coming as a substring. D is coming as a substring. BA is not coming as a substring, so BA can be my answer. These six cannot be. For AD, this AD is actually coming up in some other string, so AD can also, is it BAD? Yeah. BAD is also coming up here, so AD can also not be the answer. And similarly, for BAD is not coming up anywhere, so BAD can be the answer. Like apart from this string, BAD is not coming up in any of the other strings, so BAD can be the answer. The shorter one here is BA, so BA is the clear answer here. BA is the clear cut one. Yeah, BA is the answer here if you see. And for the last string C, it has only one non-empty string, non-empty substring, which is C, which is actually coming up in some other string. So it cannot have any answer. So we will just have an empty string. I hope that the problem is clear at the very least. Right, at the very least, the problem should be clear. We have done a trial, and I think that it has covered all the possible cases which could happen. One of the cases could have been that you don't have any string. In that case, you return the non and sorry, you return an empty string. If you have an answer, it might be the shortest string. Like you might just get a shortest string, so you will just return it. If you get multiple strings which come up as the shortest one, which are having the same length and are the shortest substrings which can come up as the answer, then you will pick up the lexicographically smallest one. So this is what we have to do in the problem. Now, how will you do it? A very beginner-friendly approach can be to, yeah, like a very beginner-friendly approach could have been that for every substring in the first string, check out for that in all the other strings. Just go on in a complete brute force way. Just check out if it is there in any other string in the complete array or not. And do this thing for each and every substring from each and every string in the array. And you can try to think about it. It is really inefficient. Like it will do the job, but it is really inefficient. So it won't work out well. We will actually talk about it, but in a different way. I have a suggestion. Like I have noticed this thing by a few contests. If you have seen my PCDs, you might have also noticed this. That whenever you have problems related to substrings or subarrays, like anything like that, why don't I just consider like um, CAB, ADBD, like um, this is the given array of strings I have. What if I consider that the problem was a bit different? What if the problem had given me um, something like this? Like instead of these strings, if it had given me a string array, an array of strings, like similarly, this thing for all of the strings. Let me just do it once. Let me just write it once. What if they had given you an of array of strings, an array of strings, है ना? Like this is a 2D array of strings, right? If they had given you something like this, and for each and every array, for each and every array, if you have to find out for each and every array in the complete array, if you have to find out um, the shortest or the shortest string, like let me define uh, this is the index 0, index 1, index 2, index 3, right? So let me define answer of 0 as the shortest string from, let me call this complete array as ARR. So the shortest string from ARR of, this is ARRI, from ARRI, which does not come in any other array of strings. So basically, if you see, I have the exact same problem which I had earlier, but this time what I have done is like I have just manipulated the problem in a different way. Instead of saying that, like instead of talking about the substrings, I'm saying that just assume if you have been given the string of arrays instead of a string from which you create substrings. If you have already been given all these substrings, obviously you can generate all these substrings from an array very easily, and you have been given such arrays, and for each and every array you just want to find out the shortest string from this array which does not come in any other string. Obviously you still have the case that if there are multiple shortest strings, then pick up the lexicographically smallest one. So the lexicographically um, like I'm not writing about that lexicographically part here, but you remember that you have to take care of lexicographically smallest string as a tiebreaker. You might ask me that what if the two strings are equal lexicographically, which means that there are two strings which are equal, then obviously you can just give any of one of the answer. Just ignore the part which I discussed. Like this is really basic, so you can ignore it. Yeah. So now the problem is, like, you just try to think about it. Earlier, whatever the problem you have, you are still having the same problem. But do you think that this one now feels a bit easy to think about? Already you are getting one intuition that for all of these strings, you can just traverse the complete array, the complete remaining array, and check out if it is coming up as a string anywhere or not. Now you don't have to check if it is coming as a substring, you just have to check if it is coming as a string somewhere or not. है ना? Similarly for A, similarly for B, similarly for C, A, B, C, A, B. And everywhere, like for all the strings which never came anywhere else, we will just store the shortest one of among them. And when there is a tie among the shortest ones, then just use lexicographically smaller one as a tiebreaker. Once you get the answer for this, do the same thing for this guy, for this array, and so on. Right. Now, the complexity here, like we are just doing the exact same thing. We have just changed the way we look at it. So here the complexity will be, we are having, oh yeah, one more thing. The array length here is n, and here like this n can be as large as 100, n is as large as 100. And for now, in the worst case, all the strings would be having a size of 20. So let us say that there is an integer m denoting 20 and n denoting 100. Like these are the worst case possibilities. So here the size of the array would be n, and the size of the sub strings can be mmm, right, in the worst case. So the number of substrings in a string is actually like in order of something, like it is something like m into m plus 1 by 2. Um, it is simple thing, you can actually figure out on your own the number of substrings from a string. So let us just call it as m square for now, instead of calling it exactly as m into m plus 1 by 2. Just I'm just calling it as m by 2, sorry, m square, because it would be in order of m square. No? So in general we can call it as m square. So these arrays would be having a size of m square, right? So for the time complexity, we are having n arrays, every array having m square size. Since you would be going on to each and every string in that array, we will have m square strings. Like these are the total number of strings in the complete array. For every string, you will check out if it is present, like if there is any other string in the complete array which is equal to this guy or not. For that, you will have a time complexity of almost this much. Like for n minus 1 people, you are having m square time. So it is sort of n into m square time complexity once again. And since you would compare if this guy is equal to some other guy or not, like you would be comparing the strings as well, and the maximum possible size for a string is m, and like it would be less than m, actually, like less than equal to m. So like in general we can say that this is the maximum possible time complexity. Let me just verify it once. Yeah. So the time complexity here comes out to be really good. You understand the sarcasm that it is very terrible. N square into m5, even though the constraints are small, 100 square into 20 raised to the power 5, it is still like really terrible. Right? We can't do it. Just forget about this. You know? You see, this is a part which you cannot ignore. You will have to check out for each and every string in the array. You cannot ignore this part. At least it makes sense to first of all just go over all of them. You know? If you try to uh, prune the solution here also, key, I will leave some strings. I will not check up for some strings if you try to find out some stuff like this one. Uh, Obviously, you can try this, but it will just make the problem complicated, and I don't think you will save much time here. But from the other part, you can actually save a lot of time. Like if for this string, if you have to check out all of these like one by one, instead of traversing the whole array of size m square, what if you store all of these values inside a map or a set? है ना? Like you can store it inside a set also. Just store all these strings inside a set, store all these strings inside a set, and store all these strings inside a set. So now instead of traversing the whole arrays, you will just check out whether it is present in the map or not. So instead of having an m square time complexity for iterating over the whole map, you will have a log of m square because of the set, and log of m square is sort of equivalent to log m. Write it in any way you want. You will still have to you will still have this big of n time for going on through the complete string. Like if you are having a string of length 20, then even when you are putting a bit inside a set, you will still have to go with its length. So if the length of the string is 10 raised to the power 5 and you are putting it inside a set, you will obviously have a time complexity of 10 raised to the power 5 into log of whatever. No? So this m is still there. Yeah, you don't really like, obviously you don't really need to worry a lot about the small part. Like even if somebody ignored this m, it is still fine. It will not really cause a lot of trouble since m is very small, but it is a good idea just to just remember it. Right. Now, can it work? Let's see, can it work? We are having n square, m cube, and log m square, which is not gonna be too much. N square will turn out to be 10 raised to the power 4. M cube will turn out to be 8,000. 8 into 10 raised to the power 3. No, 8 into 10 raised to the power 3, which is and log of 400, which would be, I guess, maybe something like 7 8, 7 8, something like that. Or in the worst case, let us say it to be 9. It would be less than 9. So this thing comes out to be something like 72 into 10 raised to the power 7, which is 7.2 into 10 raised to the power 8. We are just missing by a small amount, and like obviously it is, there is no guarantee that the worst case will happen. So this solution might actually pass. है ना? We are just talking about the absolute worst case, even worse than the worst case. So even though the solution is having a time complexity way more than 10 is the power 8, but there is still some chances of it passing. If you try to submit it, it might have passed, but we will optimize it even further. We can optimize it even further. The thing is, like till this point, it was quite beginner friendly. Now I will talk about optimization. It is not really hard to understand, but it might have not been really obvious for a beginner to think this much. That instead of going on through all of these strings for all of these sets, actually, let me just draw it once again. Like what we are doing here, we are having an array. We had an array of arrays. For now, we have actually, like, we are still having those array of arrays. We are still having these arrays of arrays, and along with them we are having some sets. For every array we are having the set of all the strings it has, so that we can very easily check if a string is there in the set or not. Now for a string in this set, I will have to actually check out for all of these sets. These are n minus 1 sets. If you have n number of arrays inside this bigger array, and every array having a size of um, m square, sort of m square. Obviously, it would be a little less than that, but overall, like, just it would be something in the order of m square. So yeah, I'm just calling it as m square. By the way, it would be less than that. It would be m into m plus 1 by 2. So maybe actually, yeah, I think that m square would be larger than whatever we have been taking. Like it would be in the same order, so we can just ignore it. Basically, the problem is if I have a string here, maybe ABC. For that, I'm going through all of these sets. I'm going through all of these sets. If you see your complexity for every string, like this much complexity is actually talking about going up for all of the strings, and the other part is checking if that string is present anywhere else or not. This big of m is something you cannot ignore. If a string is having a length of 10 is the power 5, then obviously you will have to deal with it. You cannot do anything with it. Maybe you can try out something like string hashing to make the complexity a little better, but in general it won't create much difference there also. It might create, है ना? But for now let's not go with string hashing. This part is actually talking about going on for all of these sets, है ना? And this is actually talking about checking inside a set. Now, for the login part, you cannot make it better. But this n part might be possible to make it better. This is a standard thing. Instead of like, if you let me draw it with a pen, this is the complete array you have, and for a particular string, what you want to do is you want to check out if it is present in any of these, right? So one thing you could have thought about is like it might not be really easy to think about, but if you have done this problem, if you have done something like this even once, which you are doing so that you should get the intuition from the next time, like just create a bigger set. Maybe create a set for this complete array, which will have all these, which will have all of these strings inside one set. And now remove all the strings which are in this array from this set. So now this set will actually have the strings of this whole array. This is a really good idea. This is a really good idea which can be used in a lot of problems at a lot of places. So like this is not really hard to understand, but for a beginner, I'm not really expecting that you got this idea on your own. It is good if you got it, but even if you didn't get it, it's not a problem. Now you might have noticed one problem that like in a set you don't have duplicates. So if ABC was coming up somewhere in this set, you will have only one occurrence of ABC. Like even if you pushed ABC twice inside the bigger set, you don't have duplicates, so you will just discard one of them. If you know what sets you should be able to understand this. Even if you pushed inserted ABC twice in the set, you would have got it eliminated, right? So when you remove this ABC, you might just get like you won't know if ABC is coming up somewhere else or not. Like this is something you should be able to think about. You can try to think about it on your own. I'm not really explaining it more now. So you should have got the idea that I should use something like a multi-set everywhere. So in a multi-set, like what you can do now is if ABC is coming up more than once, then in the multi-set you will have two occurrences of ABC now. Now what you will do is for all the strings in the array, you will go like from the complete multiset, from the bigger multiset. Let me call this as the total multiset, total set. From there, you will remove one occurrence of ABC. After that, like you will just remove occurrences of all of these strings first, so that all of these strings have been removed. You have only these remaining. Now, for every string in this array, you will just one by one check if it is in the total array or not. So now, in this way, you would not have to go on to n minus 1 strings. Instead, you are first of all removing all of the strings from this multiset, so it will have m square log m time. It will take this much time. Oh yeah, by the way, at the beginning, you would actually have added all of the sets at the all of these strings in the set also, so you will have that time complexity also. Like um, initially, you will have n into m square into something like log of n into m square time complexity for inserting all the strings, and after that like there is a plus because after that you would be doing this stuff. So you would have got something like big O of m square into log m time for removing all the strings from this array of this array. And after that, once you removed all of these, after that like this is in a plus, you would check out for all of these strings once again. So for m square strings, you will check if they are present in the set or not. Right now, like the size of the set would be n into m square. So you will have log of n into m square time complexity for checking for every string. And after that, you will just insert back those strings once again into the set because you would require them in the set for some other arrays. So like whatever you did here earlier, just do that thing once again. In this time, just inserting all of them again. So this complexity is a lot better than before. if you compare it with the earlier time complexity gate, unfortunately I've erased it. But if you remember that earlier I was having something like 7.2 into 10 raised to the power 6, right? I have just got rid of the go of n from multiplication, so the time complexity would, like, it won't be exactly this much. It would be something greater or less than this, but it would be something like this. Maybe less than equal to 26 iterations. Or I'm not really sure about the iterations. I have raised it, but it is not hard to find out the number of iterations it is approximately taking. This solution is actually good enough to pass this problem. And there is one better thing you can do. Doing this thing is not really important, but there is a better thing and an easier way. You can actually create a map for each and every array instead of having sets. Instead of creating multi-sets, you can just create maps everywhere. And once you have created the map, you can get the frequency of ABC inside this array from the map, and you can get the frequency of this ABC inside the complete set. So you don't really have to erase these people and then check and then put up again. You can directly check if this guy, like, what is the frequency of this guy. Let us say the frequency of this guy in this array is 1, and the frequency of this guy in the complete string is 2. Sorry, in the complete bigger array, the total array is 2. Then you know that it would be present somewhere else also, and otherwise it won't be present anywhere else. So in that way you can actually figure out whether it is present somewhere else or not. So you can get rid of this guy and this guy. It did not really make much of a difference in terms of time complexity, since this guy was nevertheless the dominant one. But the thing is, you will have to write smaller code. You will have to write easier code now, right? So now I will, like, once just tell you about the complete stuff which we have been doing, and then I will show you my code. So what we are doing here is, let me just revise it instead of writing it again. We had been given a problem in terms of substrings. We just have learned this thing from our experiences. If you have just attended the PCDs, you would have seen, like, during the PCDs, I realized that explaining the problem with by creating array of strings instead of for a string whenever you have a substring problem is easier. Like, I just realized that it is easier to explain in this way, and then I realized here it is actually able to understand as well in this way. Like, even for thinking during a contest, it is still easier. So we just manipulated the problem as, instead of being given strings, we will be given the string of its substrings. Like, you can easily create this thing, create these arrays. And now the problem is, you just want to find out the shortest string from this array which does not come in any other array of strings. Now, if you feel that substrings, thinking about substrings looked easier, then do it in that way. It is not really a problem. The idea is the same, right? The idea is still the same. After that, like, we just had to do this simple operation that for every string, we just want to check if it is coming up in any other string or not. So for every string, there will be this many strings. For this, you want to check if it is present in any other array of strings or not. For doing that, we did discuss a few approaches. I wanted to show you a few ways. Like, uh, instead of actually directly going on to the way we could have used a map, I did discuss about the way you could have got the intuition to a map. Will you go in that way? No. In future, if you get a problem like this one, you will directly go with the map. So the things which we discussed was just the base. We did discuss only about the base. Here, how will you find out if it is present somewhere or not? And we did discuss about one more thing. How are we getting the intuition of what to do? No, we actually did get the intuition in step by step. Like, we did discuss about it is step by step intuition. After this, we did realize, yeah, at the end of the day, After all the ways we discussed, at the end we realized here creating a map makes a lot more sense. So we created a map. We created a map and stored all of these strings inside a map. How much time will it take? Actually, there will be one big of m time also. So for all of the strings in the complete array, we have created some maps in which we are putting up those strings along with their frequencies. It will take somewhere around like this much complexity because this is the number of strings we have. This is the time complexity of putting up a string inside a map, and this is the length of the string which we are putting. If you can ignore this if you want, but it is a good idea to just keep it in as a reminder as well, because if m was huge, it could have created a lot of difference, and even now it is actually creating significant difference. After that, we like for every string we can just say check out in the map what is the frequency of this string inside this array, and what is the frequency of this string inside the complete array. If it is not present in any of the other strings, if it is present only here, then the frequency of this string inside this array should be equal to the frequency of this string inside the complete array. So with that knowledge, we just checked if it is present or not, and we already know what to do if it is present. Like we have already discussed this part. You can just keep track of all of these things which can be the answer, then just find out the smallest one among them, and then just find out the lexicographically smallest one among them. Right. So let me show you my code. This is the size of the array. We created a map for the complete array. By the way, one more thing. If you see, we never really had anything to do with the array. Like from this array, we just created the map and we had to do everything with the map only, not with the array. So instead of creating this array explicitly, you can just ignore this and create the stuff which you require from it. Like from this array, you just required a map. So instead of putting up all the strings inside a map, an array, and then putting them inside a map, why don't I just directly put them inside a map? I know that's what I can do, and that's what I have done. I created a map. I created a vector of maps because I need to know about every array individually as well. I created an answer vector because I will have to return it at the end. And then going on for all the substrings, like first of all, going on for all the strings in the given array. Right now, I'm talking about the given array, this one, in the problem which I have been given. From that, for a particular string, I'm going on to all the substrings inside that string, and then I'm putting up that string inside the total array, sorry, the total map and the individual strings maps. After that, I'm going on for all of the strings once again, like just going on to all of the strings, all of the given strings. Here, error I will be the string, or actually not even that. Oh yeah, like you can do that part also. You just go on to all of the strings individually and then check what is the frequency in the map and what is the frequency in the total map. Or you can do it in the way I did. Like it's not really necessary. It's not even cool. It's not even that cool. Uh, but if you want, you can actually do this thing. Just check out that. Go on to all the strings inside the map which you've put. Like for all the strings which were inside the array, I would have put up them inside a map. So I'm just traversing the map now. In the map, for traversing in the map, you know that you write something like auto and give up some name and then say string, like the map which you want to iterate, and then you talk about string str equal to it dot first and um, int, or I think it's ll, like whatever it is. I think it's int count equal to it dot second, something like this, right? Instead of writing that, you can actually iterate a map like this also, just destructuring it at this place. String comma count. So the first value, the key will be string, and well, the value will be count. I'm just checking, hey, if in the total map at str, this will just tell me about the frequency of string, like the value of the key str in the total map. In case if it is not present, it will return me 0. If you write something like str, it will also return you 0, but it will create a key value pair for the string with value 0, which will just take extra space and make your map slower. So this is why I'm doing it this way. This is something you can study about it on your own. Like, it's not really complicated. It is just a rookie mistake which many people make at the beginning whenever they study about map. And then you are just I'm having some if else conditions. I'm sure that I don't have to write up these many because I'm traversing the map. So obviously I'm having lexicographically smaller strings coming first. So I think that if I just write up the condition as um, answer length equal to 0 or answer length greater than str length, I think that this thing would have also passed if I had written only this much instead of these if else conditions. But for now, I'm just keeping this solution, which I know that it has passed. I know, not even this much actually. I had written it earlier. Like, this is a clear way of writing it. Obviously, you are good enough to write if else conditions on your own. Um, this is what I had written during the contest. It doesn't really look a lot clear. That is why I had written more if else conditions to write it clearly. Okay, I can't really go back. Anyways, like, you got the idea, है ना? You can write up if else conditions on your own also. I'm just checking if answer length is 0, it means that I have not got any answer so far. Or in case if answer length is greater than str length, it means that I have got a better answer. Then I'm just updating the answer here. And in the other case, if the answer length is equal to the string length, then I'm just saying, yeah, in case if answer is lexicographically larger than str, then update answer, else satisfied. Okay. So this is the solution for the third problem. Um, Now I think that we have already discussed about the time complexity, and space is also really easy. You just see um you are creating a map which will have like, you are creating n maps, and each and every map is having a size of m square, and you created one bigger map with um, size n into m square. You know, so just add up these. This is the space which we have been taking, and we took a big of n space for answer vector. That's it. So the space complexity is also like almost equal to the size of the strings array. Sorry, not equal to that. Actually, greater than that. The space complexity will be n into m square. The given array has a space of big of n into m. So this is the space, and for the time we have actually discussed this quite many times. So overall, the problem was implementation based. You just had to brute force the solution and optimize it a bit. It's not really optimized too much. Like, we don't really have to use any logic for optimizing. We just use some standard methods of optimizing. So many people will actually call this as a brute force method, because all the optimizations which we have done are standard. So people generally call this as brute force. Okay, so let us talk about the fourth problem now. Maybe we can have half a minute break. My throat is having some pain because of speaking so much. Okay, let me just start. Sorry about it, but I'm having cold, so I'm having some pain in the throat while speaking. So like in the problem 4, it tells us that we have been given an integer array nums of length n and a positive odd integer k. Now, like in my like first of all, let me be honest. I could not solve this problem during the contest. I did upsolve it after the contest. So I will tell you about the mistakes I made and how I upsolved it and what we should do while upsolving. Um, like at least what I prefer to do while upsolving. And the solution which, like the idea which I got in my mind did not have anything to do with positive k, and neither the solution which I used for upsolving had anything to do with k being positive integer. No, sorry, being odd. So, apart from the solution which I tell, I'm sure that there would be a better solution, a greedy solution maybe, or maybe some different solution apart from mine as well. So, I would highly recommend you to watch out some other solutions also. You will get it in Leetcode editorials, like you see the discussion tab, like you can just go there and you will find it. The problem says that we have been given an integer array n and an integer k. For now, I don't really care if it is even or odd. Like uh, the approach which we have will work on both even and odd numbers. Even if the value of k was odd, it will still work. So, like our solution is a bit more generic. Um, um, we say that hey, the strength of x subarrays is defined as an expression like this one. Basically, if you are having some subarrays like these, their strengths will be sum of one, like the sum of the elements of the first subarray multiplied with x, where x is the number of subarrays. Then the sum of the elements in the second subarray multiplied with x minus 1. Then the sum of the elements in the third subarray multiplied with x minus 2. Then the sum of the fourth subarray multiplied with x minus 3 and so on. And there is one more thing which you can notice. First, it was plus sum of 1 into x. Then it was subtracted. The sum of subarray 2 into x minus 1 is subtracted. Then for the third guy, it is added. Then for the fourth guy, it is subtracted. And so on. And they have just told what is the value of sum here. And formally, you can write strength as the sum of this guy. We need to select k disjoint subarrays from nums such that their strength is maximum, return the maximum possible strength that can be obtained, and they have given a clarification that we don't really have to select the whole, like cover the whole array with the selected subarrays. Even if you cover up, let's say if you had k equal to 3, you had just taken 1, 2 and 3, like 3 basically, even if you don't cover the whole array, it is fine. If the subarrays are like 1, 2, and 3, if these are the three subarrays you choose, it is still fine. But it will not really have the best possible uh, strength here. So that's what we have to do. Let me tell you about the basic idea which I had. First of all, whenever you see a problem, like what we always do is we just try to look up for some observations in the problem. Observations, we get some intuitions. Like whenever we read a problem, we just try to look up for some observations. We do get some intuitions. We do try something greedy generally. है ना? And when none of these works, then we try to think about brute force or trying out all possible combinations. Trying out all possible combinations. Like we have to choose some disjoint subarrays. So what if you just try out choosing all the possible disjoint subarrays or the combinations, है ना? Something like this. This is the general idea in which I do go while solving problems or trying out. Um, Here I directly got the intuition of dynamic programming, but even if I had not got it, if I had got some idea about, like if I had been trying to do some greedy work, I would have at last realized that everything can be really random. You know? So like from what I would have seen, I think that it is possible that the problem might have some greedy solution. But let us say you did not get the intuition of DP. You whatever it, observations you got from there, you just went up with the intuitions you got and you try out greedy. Let us say none of them work. Let us say none of that worked. Hmm. Then what we generally do, try to do is think about a brute force solution and try to prune it, try to make it more optimized. Like the last time, in the last problem, we did prune our solution. We optimized our solution a lot. है ना? We try to do that thing, which is nothing but just trying out all the possible combinations. This is the brute force, and from there, just try to apply dynamic programming to optimize it. Or if you get some other way of optimizing, like just optimize it at the end. है ना? That's what we try to do. So since I could not get any idea here, like I did not really try much, but I could not. Um, I just got the idea of dynamic programming, and I felt that greedy would not work, so I just skipped this part, and directly went up with trying out this part. So if you try to apply now we are actually thinking of explicitly applying dynamic programming on the given inputs. So the given inputs are, we have been given some array nums, and we have been given some integer k, which would be odd, but right now we don't really have to do anything with it. Like we will see if we can do some benefit from it being odd. And by the way, from the solution I have, I never had anything to do with it being odd or even. We have some nums array. With the DP approach, the obvious things which just directly come up to our mind is, in the given array, you can have, like since you want to have, like you're having n elements and you want to pick up uh, k subarrays from it. So one idea which I get now here is now, like again, I'm just telling honestly that I'm not really good at explaining dynamic programming. I have a different way of thinking about dynamic programming states and everything, and it's not really that easy for me to explain. So um, it might feel a bit like confusing at some places. That why am I directly going at some places? So there can be some small parts in the problem which you might feel that why did he try to think in this way only and not some in some other way. It might not be clear at some specific places. Like right now, you might have some different idea in your mind. The idea which I directly got from here is, by the way, one more thing, the problem is a bit hard, so I'm already expecting that you are maybe somewhere around expert on code forces. You are something like this, like you are at least as good as this guy. I think that the problem is intended for those people because the problem is a bit hard. So you should have a good grip at dynamic programming for approaching this problem or doing this problem, at least in the way which I am discussing. Uh, and obviously, if you are good at dynamic programming, you would have at least got an idea. Yeah, what if I just create a DP state like DP of IND and done, or maybe just let me call it as DPIJ, maybe DPIM, where I is telling me that I have considered I elements from the array. I have considered till the index I, and I have created M subarrays. I have created these, and it is storing, like dpij is storing the maximum possible strength I could obtain. So let us say, like I do go in this way. Like as I told that I have some weird way of thinking about dynamic programming. I just got this intuition directly, and I just started thinking from this way only. Yeah, DPIM can actually store that I'm having I elements and I've covered M subarrays. So basically, from the first I elements, I have created M subarrays, not necessarily covered the whole array. Like you might have got some subarrays like these. There might be some elements being left in between. It's not a problem. You're just having M subarrays, and you will store the maximum possible strength you could obtain so far. I try to think about it in this way. So now in this way, what will you require? Let me draw it like this. Let us say this is your array and you are at this position. You have calculated whatever you wanted to calculate for the previous values. Like for this array you have already calculated. Like this is how we just try to find some recurrent relation for dynamic programming. We are basically trying to find out some state, some transition. Like this is something we just assume that what if this is the state. Let us see if it works out. Why did we take this as the given like original string? Because it looks like simple. You know, in this way I just approach it. I'm again reminding that I'm not good at dynamic programming, like not really good at dynamic programming. So um, my way of explanation might not really look good. I'm sorry for that. I'm trying my best from my end. Let us say you have covered I elements in the given array. Um, Basically, you just want to find out dp of im. You have calculated the answers for these people. Now you want to find out this answer. What will be the dp of im? So how will you find it? So this is, let us say, I. One thing you can try to think is कि यार just 1 minute, there is someone at the door. Just 1 minute, I'm coming. Sorry about it, someone was at the door, so I had to go. Yeah, just 1 minute. Yeah, I'm back. Okay, so let us say I want to find out dp of im. I'm just trying to figure out a transition if uh, I can do something like this. So dp of yeah, one more thing. This dp of im, um, like what could have happened if I want that my I want I want m subarrays from the first I element. So it is possible that I might have the subarrays like this, like where the last element is not picked, or I might have subarrays in this way where the last element is also picked. है ना? There are two ways. So in the way where the last element has not been picked, it means that dp of I comma m would be nothing but, in that case, like for that case you can just say that dp of I m would be equal to dp of I minus m, I minus 1m. Basically, like if you're not picking up the last element, if you're having the subarrays in this way, something like this where you're not picking up the last element, so the maximum possible strength you could get for choosing m subarrays in the first I elements is actually equal to the um, maximum possible strength you could get from the first I minus 1 elements, because you have not picked up the ith element in any subarray. So and this thing is actually stored in dp of I minus 1m. So this is how you can actually find out one possible way of getting to the state. The other way of getting to the state is, what if there are some arrays and the last array has been picked up? है ना? Like there might be some elements being kept in between. So you are just having a sub array ending at this place, starting from some place. है ना? This is the other way a state could have been started. Let us say that the array started from here. The sub array started from here. Then, if you look at it, it is nothing but like till this point, dp of j m minus 1 would have the answer for this whole thing, right? For this whole thing, dp of j and m minus 1 will have the answer for this whole part. Now all you have to do is just find out the answer for this part, like what will be the part for this part. This Let us say the sum of all the elements in this range is sum of, by the way, j is the first element here, so it would be dp of j minus 1 m minus 1, because you want the answer till this point, है ना, from your dp, right? And this is the array you have, so you will have sum of j from j till I, because you are picking up the ith element also, being multiplied with, like you have just found out the sum. Now you know that you have already picked up m arrays, and this is the mth, like you have already picked up m sub array, m minus 1 sub arrays, and this is the mth sub array. So for the mth sub array, you will have something like this being multiplied, like for the ith sub array out of x sub arrays, you multiplied the sum with x minus I into 1. Since we have to pick up k sub arrays and you have picked up, like this is the mth sub array, so like you can try to see it yourself also. You will be multiplying sum of the sub array with this much amount, k minus m plus 1, where k is the total number of sub arrays which we have to pick. Instead of x we have a k, and instead of I we are having m here. We have denoted m as the uh, the sub array, है ना? This is the mth sub array which we have been picking up. And there is this thing also, minus 1 raised to the power I plus 1. So we will have minus 1 raised to the power, like instead of this I we have a n, we have m. In this problem it has been talking about ith um, ith subarray. We are talking about mth subarray, so we will have I minus 1 into minus 1 raised to the power m plus 1 being multiplied like this. So in a nutshell, we have understood, yeah, dp of im is actually equal to the maximum of dp of I minus 1m. Basically, I don't have any sub, like basically I'm not picking up the last element. If I don't pick up the last element, and then in that case I'm not having any new subarray, है ना? And other than this, the max of this guy, like these two things, max of, let me use a different variable. Let me call this as f of um, jm, igm, like whatever. Let me just write it completely here. I just need some space more. I just need some more space to write up the whole expression. dp of ij, like you want to store the maximum value at the dp of im, and the choices you are getting for this is either come up from this state, basically don't pick up the last guy, or if you are picking up, like if you are having up some subarray at the end, then that subarray would have started from somewhere. Let us call this thing as j. Then in that case, the dp of im would be equal to the sum of this guy, that is these people, plus for this guy you are having this. Sorry, you will have dp of im here equal to the max of dp of ij, not ij, sorry, not ij, dp of I minus 1m, and the max of dp of this amount, j minus 1 m minus 1, j minus 1 m minus 1, plus this expression, like um, minus 1 raised to the power m plus 1 into sum of j till I multiplied with k minus m plus 1, है ना? This guy, like the maximum of this and these people. This is something you can very easily find. This is something a bit challenging for us, so we have to find out this thing. Um, let us try to write it completely, like break the sum of ji with prefix m, because we will just make things a little simple for us. So let us say dp of dp of yeah, by the way, this j is less than or equal, like this is true for all j which are less than I. है ना? I think it is that, like j belongs to the range from 1. The subarray might start from 1 and end at I also. है ना? So j will be in this range. So what you want is dp of ij. No, what I was writing is, sorry, I forgot what was I writing. Yeah, I was just writing up this expression once again, making this expression a little simple for us. So dp of j minus 1 m minus 1 will still remain the same, but this expression of sum j minus, like sum from j till I, is nothing but it is the prefix sum till I minus prefix sum till j minus 1, right? This is it. So you can write it in this way, like minus 1 raised to the power m plus 1 into pre of I into k minus m plus 1, and minus the other part, which will be minus 1 raised to the power m plus 1 pre of j minus 1 and k minus m plus 1. Now like if you see that you are having minus 1 raised to the power something and then minus 1, so you can just write it as uh, basically just multiply it with minus 1 once again, so you will have minus 1 raised to the power m. Basically I just removed this minus sign with a plus sign and changed this from minus 1 raised to the power m plus 1 to minus 1 raised to the power m. Things just remain the same. I have just written it in a little different way, and now you can see like we just simplified this. We did not do any rocket science, we just simplified the stuff a little bit. Instead of this I wrote this, and here is one observation you can make, that this person, like this guy, does not depend upon I. Here j should be less than equal to I, but even if um, let us say we were having an I here, and like we were talking about all the j, like we were talking about all the possible values of j from in this range, है ना? So even if I had an L here, all of these people will still remain the same, है ना? If I just call this thing as val of j comma m minus 1, maybe something like this, um, maybe j, maybe if I just call it something like val of j comma m, which gives me this amount, dp of j minus 1 m minus 1 plus minus 1 raised to the power m pre of j minus 1 k m minus 1. If I just pre-calculate this thing for all of these j's, then I can say um, like my dp of I here would be, dp of I m here would be equal to max of, right now I'm writing only this expression, like obviously this thing will be there, but I'm talking about only this guy. We are just like pruning things. If you see, I'm not doing any arbitrary stuff. We are just trying to manipulate the stuff in some different way. Obviously, since I have already done the problem now, I'm not really going in the wrong direction, not really showing you the wrong way of solving the problem, and then after spending 10 minutes realizing that it doesn't work out. Instead of that, I'm just directly going up in the way which from where we could get the solution. Yeah, obviously after just looking at the solution, you will still have to spend a lot of time on your own to think about how you will get the intuition for from the next time. Like I also do the same thing. I also do the same thing, that whenever I see someone else's solution, I try to identify that from the next time, when how will I get the intuition, how will I get such intuition. So we got such intuition here. just recapping a bit, we got the idea that for this kind of a state, either you pick up the last guy or you pick up, sorry, either you just don't pick up the last guy, you just skip the guy. So you will have till this point, like the answer till this point being like dp of im would be equal to the answer till this point, which has already been stored. Or the other thing which can happen is you might just have a subarray ending at this place, which would have started from some j, and here j should be less than equal to I. So yeah, by the way, one more thing, like till this point, if you just talk about the problem till here, you will definitely get the answer. Like we have actually, yeah, I think I should have discussed this earlier. That till this point, when we came up, we had actually got a transition for every state in big O of n. We are having n square states and we have a transition of big O of n. So the solution will be big O of n cube. This will not pass the solution. Oh, sorry. We are having n into k states. So the complexity is n square into k. This will not pass the solution, but it is a good enough time complexity. Like good enough. At least we have been able to get the solution now. We have got the DP state and transition to get the solution. Now what we want to do is just optimize it a bit. Sorry for my mistake. I should have discussed this thing first and then try to optimize it. But the thing is, we can't really submit big of n square into k. So we try to optimize it. We saw that um, like maybe first of all just make the expression look simple. Just um, make I and like j and I appear differently, because here you see that after breaking out sum of j to I, like the elements from j to I as this guy, now these two expressions does not really have any dependence on each other. The only thing is that you will be talking about j being less than I, but um, like we have to find out the max of this expression for all j belonging to I from 1 to I, and this expression does not depend upon j. So you can write it differently now. Like let me just show you first of all, like this whole expression can now be written differently, like partition it in a different way. You can call it as dp of j minus 1 m minus 1 plus minus 1 raised to the power m p of j minus 1, right, and k minus m plus 1. This expression does not depend upon I, plus minus 1 raised to the power m plus 1 pre of I into k minus m plus 1. So when you come up till this expression, would you already know here you will get such expression which looks so awesome that two of the people does not depend upon I and the third person does not depend upon J? No, we did not really know about this earlier. But once you wrote the expression, you saw something like this. Now this is something I missed out. Like here is the place where I missed out, and this is something if I had noticed, I might have been able to solve the problem during the contest. But after the contest, I asked with a friend and he told me about it, and then I realized, yeah, I missed out this observation, this important observation here. Now what you can do is you see that this thing is not really yeah, one more thing, like since I could not notice something like this here, what I had been trying to do is I was during the contest I was trying to like use something like a segment tree. I was just identifying if I can use a segment tree to make this thing work in something like big of login, if it is possible to make it work in login or not. But I could not do this thing. You can also try it out, like assuming that if you are attempting a contest, you might also get such intuition. I had also got the intuition. One mistake I made is I just went the whole time at this. I should have stopped. I should have at some place identified here it is not gonna be done with segment trees, and I should have come up at this place. Maybe you can also try to identify that at what place you should have stopped. whenever you are solving the contest. This is the observation. Like the thing is, if you are having n into k states, here we are having n into k states, and every state you have a big of n transition. Either you try to like make the transition cheaper, maybe something like login, which we can't do, or you try to like find out the optimal answer for more than one state in this time. Like there is some problem in at coded DP also. I'm not really sure which problem, but it is something related to children in candies, I guess. You can find it around L like JKLM. I think you can find it around the JKL task, somewhere around this much task. Go to at coded DP contest. Like for those who don't know about it, go to at coded DP contest, and there just search about it on internet. You will get some link there. Just see the JKL, like do problems till that point. I think solving problems till L or M makes more sense than attempting this problem in a contest for now. First do those problems. You would have seen, like if you do them, you would actually see a way, like a problem in which you have a big of n transition where you get answer for n states, right? So if you can't optimize the transition, then you should look up for this kind of a thing, which we have been looking up for right now. Um, we have actually made the transition, like we will just want to find out the max of all of this for all j in the range from 1 to n, 1 to I. Now this expression does not depend upon I, so you just want to find out this thing. This thing depends upon j and I, j and m, है ना? This depends upon j and m. So maybe let me call this thing as val of jm being equal to this guy, है ना? Maybe let me call this thing as this. So for calculating like dp of im, what I can do is, first of all, I calculate this guy, and then maybe let's say I create a Maxwell array where Maxwell of jm actually stores the max of val of 1m, like max of val from val 1m till val of jm, something like this. Basically, it is a prefix max array of this array. You could create something like that, or just at the end replace this array by its prefix max. I did that thing. Not too complicated to think. Maybe since a lot of things are really vague right now, you might feel it a little bit complicated, but it's not. This val array is not complicated. So what you can do is, you see that dp of im can actually be said as the max of dp of I minus 1 m, and like let me just define this Maxwell once more. Maxwell of jm stores the max of val of maybe let me use a different variable L comma M for all belonging in the range from 1 to um, j. If I do something like this, then in that case, like if you see in this expression, all I wanted to do is I just wanted to find out the max of all of these, right? I just wanted to find the max of all of these, which I can just get it from here. Like if I find out the val array, then finding out this is not really hard. So I can just say that my dp of I m would be equal to max of dp of I minus 1m, and the Maxwell of this jm, sorry, not j, instead of j you will have an I here. because you just want to find out from 1 till I, है ना? And uh, along with it, you will have this expression coming up here. This expression is not really hard to find out. You just like you can pre-calculate the prefix sum array. You can like you already know about the value of k and you already know about the value of m for the DP of the state, and you already know about this thing also. So this is something you can just count once and just add it here. So this is how you can find out the DP state. For finding out this thing, you will actually need to find out this Maxwell array. है ना? You will need to find out this Maxwell array, for which you will have to find out the val array. So for finding out the val of, like I think we have written it somewhere. Yeah. For finding out the val of j comma m, you need to know about the j minus 1 and m minus 1 thing. And this is something you can already pre-calculate. So it makes sense. Like for finding out dp of I m, if you are see if you are writing recursive code, it's already fine. If you are writing recursive code, you don't really need to worry about the stuff which I'm discussing now. You can just like you know about the states, you know about the transitions, just go on and write up the code. You will be able to do it. But for the iterative code, if you are writing iterative code, then you will have to worry about it. For finding dp of im, you need to know about dp of I minus 1m. है ना? You need to know about this because you are using it. You need to know about Maxwell of IM, and the third thing is just something like you can already pre-calculate the prefix summary, so you don't need to worry about this. But you will have to find out dp of I minus 1m, and you will need to know about max of 1. Like we have for the transitions part, we have already been done. Now we are just trying to identify here in which way I have to run the for loops. So for finding out max value of IM, it basically means that you will have to find out dp of, like you will, for finding maximal of IM, you will have to edit. Let me just this. We need this guy, and you need Maxwell of IM. For Maxwell of IM, you need to know about val of 1m, val of 2m, val of 3m, and so on. है ना? Like and so on till val of IM. For finding out val of 1m, 2m, IM, and like whatever, you will need to know about dp of uh, like for a particular j it was j minus 1, so for 1 it would be 0 on m minus 1 and so on. Like in general for an I, in general you will say here you will need to know about dp of I minus 1 m minus 1 for a particular I. And like everything will just remain the same. Obviously, it might look up a bit complicated to uh, to you if you have never done something like this. We are just trying to identify that what states should I calculate first, because my this state is depending upon this value. So if I run up a for loop in such a way that this guy comes first, then like I will not be able to find out the answer. So here you can just see, yeah, I need to know about dp of I minus 1 and m minus 1 before dp of im. So it is a good idea to run up a for loop from I from 1 to n, 1 to n, and for m from 1 to k, like in this order, or maybe in the other order as m from 1 to k and n from 1 to n. Now, in my code, you will see that I have used this one. I did not really, um, like, I have not tried to see here, will it fail or work? This one looks a bit more intuitive. Why does it look a bit more intuitive? Because if you see, for finding out um, like in all the equations you see, you're always having, for m, you're always having just m minus 1, right? You're just having m minus 1 coming up here, or m coming up. Like, but in case of I, it can be uh, anything. Like you will actually need to know about all the DP states here. DP of 1 m minus 1, DP of 2 m minus 1. You will need to know about all of these. So this is why I felt the other one to be more intuitive, and the one who had written the solution had also written the deep solution. Uh, but this might also work. Like like this way might also have some solution. You can try to think about it. This is something like a theory you can have. I will also try to think about it after the PCB. Like this is the way we improve. We try to think of the things we are not really sure about, so that we either learn something or we get to know that we were correct or wrong, like whatever. So for now, the idea which we have got is um, for any ij, when you're talking about dp of im, you have got one way of coming to this place by dp of I minus 1m. So one possible value of dpim is this, and the other possible values is um, Maxwell of im plus some expression which is something you can easily count. You can easily find out that thing, like the maximum of both of these. For finding out this guy, we will have to find out the val of 1m, val of 2m, and so on. And one thing which you can do is, if you run up a for loop from of m from 1 to k, then first of all you can pre-calculate the values of val from 1 till n for all m, and after that, like it will be done with a for loop. It will be done with a for loop, and then in the other for loop you can just have for I from 1 to n. Uh, by the way, once you figure out this val, if you want, you can just directly say val. Like if you want, you can create a Maxwell array, or just find, like, just store the prefix max in the val array itself. So you will have uh, like, instead of, for now in the pseudocode I'm just writing Maxwell here. You can just run up another for loop, or just in the same for loop you can just find Maxwell for all from one, from this guy, you know, for all the possible values of 1 till n. Then here you can say dp of im is equal to maximum of dp of I minus 1, which would have been calculated in the previous iteration of I, and um, the Maxwell of I m. Now notice this part. For all of these, for this whole for loop, yeah, let me just complete it once. We will have some expression which can be calculated in big of 1. So now notice, for every addition of this loop, it is taking big of n. So big of 1. So for the whole for loop, it is taking big of n here, because of this pre-computation we did for this. So basically, in big O of n total time complexity here, in total big of n, because this is also something big of n, this is big of n plus big of n is big of n. So in total big of n time, you are actually updating n states. You are updating n states, and you are doing this for k times. So your overall time complexity will turn out to be big of n into k, and the space is also big of n into k. I'm about to show it. And before that, I hope that the logic made sense. I tried my best. Now, I agree that the um, explanation might have not been up to the point because of two main reasons. The first one is DP is already a topic which is hard to visualize. So it is hard for me to show you in a way that you can easily visualize. है ना? It is hard for me to show it in a way that you can visualize. So explaining DP is basically, like, explaining DP is also hard. This is one problem. At least I feel that explaining DP is hard. And the other thing is I could not solve the problem on my own. I could not solve it on my own during contest. So since I had looked up at someone else's solution, there might be some things like I have not really got a lot of time to think a lot on my own after the watching the solution. So there are some chances that I might have missed some obvious, like some path which looks obvious but leads to a bad solution. So you might have still got some doubts remaining about them. I'm sorry about it, but I tried my best, I guess. Like I can't really, uh, like I could not do the problem on my own during the contest. So that's what I did. Let me show you that code now. By the way, here we are just um, using LL equal to long, so that like wherever I write LL, it will just replace it by long on its own. Um, it is just done to keep the code look a bit short. You would have definitely done something like this if you do computer programming. And similarly, for instead of writing 1e17 again and again, I have just created an integer, sorry, a long variable within INF. First of all, I'm just creating the prefix sum array. I'm notice that I'm keeping one based indexing. You can keep zero based indexing, it is fine. But the problem had one based indexing, and sometimes it looks easy to prove it one based indexing because you just do it in the same way the problem has been given. You know, you will not really have to worry about uh, you will not really have to worry about plus one minus one sometimes because of keeping things in the same uh, one based indexing as the problem has been given. And here I have created a vector of long variables dp with the dimensions n plus 1 k plus 1, again keeping things in one based indexing. For the base case is for m equal to 1, like from somewhere you have to start. So for that we have manually done it. It is quite obvious. Um, it will be nothing but the maximum subarray sum, like for every I, comma 1. Like it would be either if you just know key. If you know that from the subarray you have to pick up till I, you have to pick up only one subarray. Now that subarray might, like you might be picking up the last element or you might not be. If you are picking up the last element, like if you're not picking up the last element, in that case your answer will be equal to dp of I minus 1 because you have already calculated till I minus 1. You know. In the other case, if you have been picking up some subarray which is ending at index I, then in that case you don't really need to run up a for loop to find out the value of j. You know that you will run it from the place, like if the minimum possible prefix sum is till this point, then you will leave only this prefix, right? Maybe like let me explain it once more. What you want to do is you just want to pick up one subarray. You just want to pick up one subarray till index I. It doesn't matter which elements you pick up in it. You just want one subarray. So it is nothing but we are finding maximum subarray sum. And actually think that if you are coming up for this problem, you would have already means you would already be you are already skilled enough to do this problem. But let me still tell a bit. This dp of I would be like dp of I1 would be nothing but for the case where you are having some prefix till this point, it would be nothing but the maximum of p of I minus 3 of j minus 1. This thing being multiplied with k because initially k minus m plus 1 for m equal to 1 is this one, like k minus 1 plus 1 where m is 1 would just come out to be k. So just multiplied with it. Now for every I, if I just know that yeah, I will want to have the smallest value here. So I can create a variable in let's say mn ref. In that I can just keep track of the minimum possible prefix till now. I will just remove the minimum possible prefix from here. So, in this way, I can find out the base case. Now, this is also something not really hard to understand. Uh, so, you can actually try to think about it in case if you did not understand by just listening. Try to think about a bit more about it. After that, for finding out the other DP states, this is what I want to find out. DP of IM is my goal. At last, I will just return DP of IM. You know, DP of IM, for finding out DP of IM, I wanted to find out, um, like I had written it somewhere. Yes, yeah. I wanted to find out this guy, which I would have already calculated because I'm running on a for loop like this from smaller to bigger. So this state should have already been calculated. And I need to know about Maxwell. For finding out Maxwell, I need to find out the value of all of these people. So for that, I have run up a for loop where I'm calculating the val of j, and actually, like in the explanation, I use the word name, like I use the name Maxwell, and like I had been talking about two variables Maxwell and well, but in the code actually I'm having only val variable, which is doing the job of Maxwell. It is having the maximum of all the numbers which are smaller than that as well. Like if the max of like val of j minus 1 is smaller, greater than val of j, then it will have its value equal to this. So basically, instead of instead of calculating val and then calculating Maxwell differently, I'm just directly calculating Maxwell, and in the code I have named it as val. In the explanation we called it as Maxwell. Here we are having it as val. So I'm running up a for loop. This is the value of p, like the expression which we had here. Like the val was having two parts. The val of j comma m has two parts, this part and this part. So I'm just having the other part written. This is the other part written here and variable p. Like I just named this thing as p. You can name it anything. And then I said here val of j, this val of thing. Yeah, but one more thing. Since I had nothing to do with val of j, like val of j comma val of jm outside the like the thing is val of jm has no dependency on an expression like basically how to tell. See, for a fixed m, for a fixed m, val of j m depends only upon the val of it depends only upon the val of maybe let's say lm, where L can be anything smaller than equal to j whatever, but here you will have only m. You will not have an m minus 1 or anything like that. So instead of creating a 2D vector, I'm creating 1D vector every time in every iteration. It's a case what you can create 2D vector also. Now for every iteration here, I'm storing the value of p here, this expression, and we are having the value of j equal to the maximum of this guy, like you can understand it on your own that it is nothing but whatever we want to do with Maxwell, I'm doing it directly. Now for dp of im, it is either equal to dp of I minus 1m or it is equal to some expression which I have stored in p so that my code doesn't look ugly, plus val of I plus may val of I, um, which is the maximum of all of that which we have calculated earlier. And at last, I'm just returning dp of m. So I hope that this solution helped you even a bit. And make sure to look at the editorial of the Leetcode contest because it might have some other solutions since they actually talked about um, k being odd. In our solution, uh, we wrote a solution which does not really need k to be odd. Even if k is even, our solution will still work. We wrote um, a more reliable solution maybe, but a bit more hard to understand. Probably there should be an easier solution with which has k being odd. I will also check out this after the PCD. And in case if you have any doubt, you can ask it in chat. I hope that um, at least the problem should be doable now. If you are seriously willing to solve the problem and not just watching videos to get this solution, if you are really willing to put up efforts, I believe it should be doable now. So that's it. I'm ending the session for now. And we have already talked about the space and time complexities. Both of those came out to be because n's into K, right? So thank you for watching the video. Bye bye.